Welcome to Study Loop.
This is the answer to Chapter 21, problem number 76 from the Smith Organic Chemistry textbook. This problem talks about salsolinol, which is a compound found in some foods, and in this instance made from dopamine and acetaldehyde in the human body. And so we're asked to draw a stepwise mechanism for the formation of salsolinol from dopamine and acetaldehyde. And so that is going to look like this. So dopamine, as the name implies, has an amine in it. And that amine has a lone pair. And that is going to be our nucleophile to attack the aldehyde and acetaldehyde in the first step here. So after that nucleophilic attack, we get to this point. And so since the ring here is not participating in the first several steps of this reaction, I'm just going to abbreviate it. Right. So that gets us to here. So there are some charges here. So the oxygen is going to have a negative charge on it because it only has one bond. The nitrogen has 4 bonds, and so we'll have a positive charge on it. And I should specify, so one of these is a hydrogen, obviously, and the other is a methyl group. Okay, and so from there, we can alleviate both of those charges by doing what would formally be a proton transfer. So just for ease, we can write it looking like this. It's probably instead going to involve like deprotonation of the nitrogen and then protonation of the alcohol, or vice versa. But since it is just a formal proton transfer, we can draw it like that. So that's going to get us to here. Methyl group, hydrogen. All right. And then so from here, the next step is going to be protonation of that alcohol. So we are told in the problem that this is happening under mildly acidic conditions. So we can just draw a proton. You could draw H3O if you're more comfortable with that. It doesn't matter. And so one of the lone pairs on this alcoholic oxygen will grab that proton. So this is now OH2, obviously a positive charge on it because the oxygen has 3 bonds. And so that's going to leave. That carbon-oxygen bond will break. Simultaneously to this, the lone pair on the nitrogen can attack this carbon, which would be a carbocation if we were to draw this as 2 separate steps. But it's actually a concerted step, so they happen at the same time. And so now I do need to return to drawing the whole ring because now the ring is going to start participating in this reaction as well. So here's our 6-membered ring from the dopamine. And I'm going to change the orientation a little bit of the way that I drew the nitrogen. So there's our nitrogen. And it is now double bound to this carbon. Okay. And the nitrogen is going to have a positive charge on it because it has 4 bonds. And so since this is an imine or a protonated imine, what can happen now is the lone pair, or pardon me, the electrons of this double bond can act as a nucleophile and attack the carbonyl carbon. One of those double bonds will break, taking the electrons up to the nitrogen. This also relieves the positive charge on the nitrogen. So there is some driving force there for this to happen. And so that is going to give us formation of our second ring here. So after that step, what we have is going to look like this. So it will now be a bicyclic system with one of the rings being nitrogen containing. We'll still have 2 double bonds there. And of course, these hydroxy groups on the ring that started from the dopamine. We'll still have a methyl group there. Can't forget our proton on the nitrogen. Okay, so I'm just going to draw that hydrogen there, and the reason why will be apparent shortly. And we're also going to have a carbocation on this carbon because it was part of the double bond. The double bond broke to attack the carbonyl in the previous step. And so now there's a carbocation there. And in order to relieve that, we can use some water floating on by. And so the lone pair, or one of the 2 lone pairs on the oxygen in the water, can grab that hydrogen. The electrons of that hydrogen can go to form a new double bond to relieve that carbocation. And that's going to reform the aromaticity in our ring, which is, of course, an important driving force. And so that is going to get us to our final product. What is it? Salsolinol. Oops. So there's a nitrogen. Oh, that looks ugly. Right. So this ring has the nitrogen in it. Methyl group there. We've reformed the aromaticity in that ring. 2 hydroxy groups. Yeah, and so that's our final product. That's salsolinol, which we were asked to draw. This is the stepwise mechanism for that. It's just an amine attacking an aldehyde, and then moving some protons around, protonating an alcohol so that the alcohol will leave, and then nitrogen attacking the susceptible carbon as that alcohol leaves. And then a double bond acting as a nucleophile to add into a protonated imine. Yeah, and then just removal of a hydrogen to reform a double bond and reform aromaticity in that 1 6-membered ring. And that's it. And so that's the answer to chapter 21, problem number 76.